Hello everyone, we have seen some dynamic inversion concept last class. We will continue discussing further on that topic and then try to see some of these difficulties and possible remedies and things like that. But before that we will have a quick review of what we discussed last class, and that is how the topics are organized, something like that. We will quickly review some sort of a summary of DI design or dynamic inversion design. We will again list out the advantages associated with that, and because of these advantages we do not mind for these issues and rather hunt out for possible remedies instead of giving up actually. So, that is the way we will discuss in this class. So, quick review of what we have discussed already last class. This is the summary part of it. So, philosophy of dynamic inversion is like this. We carry out some sort of a coordinate transformation such that the nonlinear problem appears to be linear in the transform coordinate. It is not linearization per se, but we just do some sort of a nonlinear function mapping business. So, that in that new coordinates problem appears to be linear. Okay. Then once the problem starts appearing to be linear, then we know linear control design techniques. So, we design the control for the linear looking system. Again, this is not a linear system, but it just appears to be linear, that is all actually. So, using that linear looking system, we design a controller using the linear control design techniques, and once you are done in that coordinate frame, we want to see what is the controller in the original system. So, we do some sort of a inverse transformation actually. So, obviously, this design philosophy holds good if and only if the inverse transformation is possible actually, okay, and there is a unique inverse transformation, that is also an issue basically anyway. So, anyway, so this so intuitively what is going on here is the control design is carried out by enforcing some sort of a stable linear error dynamics in the transform coordinate frame. That is the bottom line actually. Now, how do we do the mathematics part of it? Something like that we discussed last class. In general, the nonlinear systems can be described system state equations like this: x dot is f of x u, y is h of x, where x u and y can be of different dimensions actually. X is state, u is control, and y is the performance output actually, which also is a nonlinear function of states. And the goal objective, we want to assure that this performance outputs should track some desired output, that is y should go to y star as t goes to infinity actually. So, and the assumption here is y star is a smooth vector actually, that means y is continuous and y dot is also continuous at least. And then special class, I mean this itself is a little kind of complicated system dynamics and all that. So, we do not I mean it is possible to deal with, and then people have concentrated a lot of attention for designing controllers for this class of generic nonlinear systems. But in this particular lecture we will confine ourselves to a class of problems where we take this control affine systems where control variable appears to be linear, and in addition to that p is equal to m, that means the dimension of u and y are same. That means in input output sense the system is a square system basically. And this g y of x, which we will define in the next slide, is non-singular for all time, because we need a matrix inversion for this matrix. G and g y are different of course, they are related, but they are different. So, what is g y? We will see that in the next slide anyway. So, this is our objective, y should go to y star, tracking objective, and we concentrate ourselves to control affine square, and for which g y of x is non-singular for all time. So, how do you do that? So, for assuring that we will first do what we did is we derived this y dot, and because y is h of x, so y dot is del h by del x into x dot, and x dot is that. So, we substituted that and then defined what is f y and g y. So, f y is del h by del x into f, and g y is del h by del x into z. So, that is g y actually, and del h by del x is defined in this matrix actually. Okay, so, that is a Jacobian matrix sort of thing. So, this matrix g y of x needs to be non-singular basically. We will see that in the next slide why it needs to be like that. So, our objective is that y should go to y star. So, we define an error vector which is y minus y star, and then make sure that e goes to 0 asymptotically. And how do you do that? We do that by selecting some sort of a fixed gain k with a positive definite matrix, such that this error dynamics is enforced, and we know that once this error dynamics is enforced, the solution is like this, E equal to exponential minus k t into E 0, and because k is a positive definite matrix by selection, it needs to go to 0 actually. Okay, so S t goes to infinity. Remember that this, first of all, this t goes to infinity is mathematical notion, and for practical problems this t goes, I mean this infinity and all that is largely dictated by the settling time that we select actually. Okay. So, if the settling time is small, that means the tracking happens in small time and things like that. And also second point is this positive definite gain matrix need not be constant. In some applications you can have limited gain scheduling as well, that is also an option, provided we really need that. Most of the time it so happens that we may not need that actually. Okay. Then okay, this is what the objective was. So, what do we do to enforce this error dynamics? We substitute this equal to y minus y star. So, E dot is y dot minus y star dot E y minus y star. So, enforce this error dynamics, and then y dot is something that we derived here. Okay. So, y dot we substitute, and then try to solve for a controller u. So, that is how you get a control thing. Control, I mean it is a nonlinear function for control. Okay, that is what we obtain with a fixed gain k. Okay. So, this controller is I mean this formula what you see here is once you start using this essentially satisfies this equation, hence this equation and hence that one. That means this E dot plus k is continuously enforced actually. Okay. So, that is how this control design works. We discussed many details on that last class actually. And usually the way to select this gain matrix for the first order dynamics is like this. Okay, you select k equal to diagonal 1 by tau, because if k is a diagonal matrix, then eigenvalues are diagonal elements, and then they are certainly positive for positive tau, and then it needs to be positive definite actually. Alright, so this is how do you design that. Now, the question here is do we always enforce this first order aerodynamics? Certainly not. So, this is dictated by what is called relative degree, and the relative degree is defined as the number of times the output needs to be differentiated, so that the control variable appears explicitly. That means, each of the output vectors, I mean each of the component of the output vector, you can keep on taking derivatives, and in each of the component of output vector will at some point of I mean derivative, and I mean this control variable start appearing, and that becomes a relative degree for that particular component of the error vector, I mean this output vector, and that is called the relative degree, and the total relative degree is just addition of those individual relative degrees by the way. So, what you are assuming here is each of the component of this E satisfy the same order. Okay. If it happens, then you can vectorially represent this equation that way. So, instead of first order aerodynamics, you can try to I mean enforce the second order aerodynamics instead, where kV is can be selected that way, and Kp can be selected that way. So, that each of the individual component wise it becomes a standard second order aerodynamics in the form of E double dot plus 2 zeta omega n the E dot plus omega n square E equals 0. That is a very standard aerodynamics or linear system that for which you know the solution behavior and things like that. So, obviously, this Kp and Kv can be selected this way diagonal I mean diagonal matrix manner, and this zeta and omega n can always be selected from performance specifications, like again like settling time, percentage overshoot, like that for each individual error channel actually. Now, we also discussed when the dynamic inversion does not work, when does it fail. Okay. So, for understanding that we also discussed that this the fundamental principle of dynamic inversion is to differentiate y repeatedly until u appears in a single input single output sense, and then design u to cancel the nonlinearity, all that we do, and then simultaneously it enforces some sort of stable aerodynamics actually. So, is it always possible to design u this way? The answer turns out to be not necessarily true, and it is possible I mean only if the relative degree is well defined actually, and to understand what is well defined we need to see this what is undefined relative degree, and this definition turns out to be like this. It may so happen that upon successive differentiation of y, u does appear, u appears, however, the coefficient of u may vanish at x, whereas it arbitrarily close to x 0, okay, it does not vanish. It only vanishes at selected points x 0, but very close to x 0 it does not vanish actually. So, how do I mean just to understand this as a small example, this x 1 dot x 2 dot is something like this, okay, this if you take it that way, then y, let us say assume that x 1 square, then y dot is like this, y double dot is like that. So what happens here is, if you can rearrange this term and it turns out that f y is like this and g y is like that. So as x 1 is 0, then g y of x turns out to be 0. So the entire x 1 0 line, the entire x 2 axis, g y x is actually 0, but the moment you go a little bit away from that, 2 x 1 is non-zero actually. Okay. So that means at x 1 equal to 0, the relative degree is not defined obviously. Okay. So how do you circumvent this problem? Probably you can go back and think, okay, let me select a different y equal to x 1 square is not good. So let me select x 1, then what happens is, if you do the double derivatives and all that, the coefficient of v is 1, which is non-zero throughout actually globally. So if you select y equal to x 1 for the same problem, the relative degree is well defined, but if you select x 1 square, it is not defined actually. Okay. So this is how you can think that, okay, the relative degree is defined, well defined, then you can talk about doing dynamic inversion. If there is a problem for that, then I may not be able to do that actually. So the advantage is what we summarized last class. It turns out to be a very simple design, because there is no need of tedious gain scheduling in general. Sometimes you may need, for very challenging practical applications, you may need a small amount of scheduling. For example, in missile guidance, sometimes people do limited scheduling based on some sort of maneuverability actually, maneuver capability. They calculate how much you can maneuver at any point of time and make the gain as a function of that. But it is very, only when it is absolutely necessary, otherwise it turns out that gain scheduling is not required actually. Okay. So it is also sometimes called as universal gain scheduling design, because just by selecting one gain, you are taking care of the entire domain of operation actually. It is easy for online implementation, because it is a closed form solution after all. There is no iterative solutions involved here. You just keep on evaluating a formula once you know the information about the state. Then always there is asymptotic or other exponential stability is guaranteed for the error dynamics. As far as output tracking error is concerned, that has to go to 0, rather asymptotic or exponential way, and instead that is true globally also, because what you are doing here is linear system aerodynamics, and that is nothing to do with local stability. Okay. So global exponential stability for aerodynamics is guaranteed as far as output tracking is concerned, subjected to obviously control availability. If your control is saturated, that formula is no more valid anyway. And we also discussed last class that there is no problem if the parameters are updated. That means if your design changes or goes through modifications and some values of the parameters are changed. If you have opted for a purely linear design followed by the standard classical gain scheduling, then you have to go back and start from the beginning, because your potentially your AB matrices all over are changed actually. Okay. But here it does not happen that way. All that you have is a formula, and that formula needs to be evaluated with respect to the new set of parameters basically. So you may still need to tune your gains a little bit here and there, but normally this does not require too much of exercise. So that scalability of design, or that what you call rapid prototyping and things like that, it is very easy actually. That means once you are very comfortable with this kind of design, then you can go from, you can very quickly synthesize your controller for the entire system, for the entire flight envelope actually. Okay. So these are the big advantages of the dynamic inversion design, and hence we do not mind looking at the possible issues and trying to hunt out for remedies actually. Okay. So those are the things that we will discuss next in this class. This up to now is all summary of what we discussed last class in detail. So issues and remedies in DI design. Okay. So let us talk about that. Just to summarize, there are potentially you can think about 4 or 5 issues, and then first issue that comes to mind is, does the inverse exist for all time? Okay. We always said, if you go back to this final formula, there is a matrix inversion, and even if the matrix may exist, the inversion may not exist actually. And what you are demanding here is that this matrix remains non-singular for all time, because x is a time varying function, x varies with time. So gy of x is a time varying matrix actually. So will it remains non-singular for all time? That is the first issue. Okay. Now, what if the problem is non-square? So, we have conveniently assumed before that P equal to M, that means number of outputs are equal to number of inputs. That is why Gy of x turns out to be a square matrix. If it does not become square, you cannot even talk about inverse actually. So, what you do in those situations actually. Then there are two big issues in DI design in general. Even if these two are taken care, the third issue is what about this internal dynamics. That means, what you have done is making sure that y goes to y star. In other words, y minus y star error, that goes to 0, that is all right actually. But also remember that dimension of y is much lesser than dimension of x normally. So, we have in this design make sure that everything remains very good in the output space, that means in the subspace of the problem basically. So, what about those n minus p dimensions actually. Okay. So, the dynamics of the system do exist in those directions, those dimensions as well. So, what about that dynamic? That is something called internal dynamics, because that is not coming into picture of this y dot expression, the output dynamics actually. We will see that is internal dynamics. And the another big issue, it turns out that it is any design that you propose, any control design should have a good amount of robustness with respect to modeling errors, because no modeling can be very perfect. We all know that there will be modeling inaccuracies and things like that. And it unfortunately turns out that this particular design is sensitive to modeling inaccuracies. Okay. That means, if you have parameter inaccuracies, or if you some terms that you missed out in the model and things like that, then it is typically not very robust actually. So, these are the reasons why, this particularly this is probably the most important reason why for many years this design was not very popular actually. Okay. But people did not know how to handle this anyway. Alright, so we will see these issues one by one and try to see some sort of remedies and all that philosophically. Okay. Some things we will tell precisely, some things we will leave it to further discussions in subsequent classes actually. Okay. First thing is, does the inverse exist for all time? As we discussed, not necessarily. So, this Gy of x inverse that you have taken care, that you have used need not admit an inverse for all time. Okay. Now, there are two issues. So, one thing is it may not admit, it can become singular for a longer time, okay, or it can singular for a smaller time, intermittent times actually. Okay. So, if it happens to be for a longer time, then probably there is something wrong in the formulation itself. We need to go back and see whether that is what you have actually formulated is right or wrong actually, and most likely it will turn out that the entire formulation somehow is wrong. So, we need to do something else for that. For example, if the controllability is not there in the plant, then it will turn out, it will pop up that these kind of issues will be quite large actually. In other words, if your controller is less effective for the output objective, whatever objective is there, then it may not, it may struggle to do that, and hence it will not be able to do that actually that way. Okay. So, for example, if you want to roll an aircraft, by limited coupling you can also use rudder to roll the aircraft, but primary control surfaces are ailerons actually. So, for some reason, if ailerons are not functioning properly, they are stuck or something, only for a very small amount of manipulation you can do using rudder actually. Okay. Otherwise, if you really want to roll it very large quantity and all, rudder will go to saturation, and then this matrix inversion will go non-singular, this matrix will go singular and things like that. So, that is a fundamental problem there. Now, what if that matrix inversion happens to be singular for small intervals of time, and for that the engineering solution tells that okay, we do not have to update your controller unless otherwise this condition holds good actually. Okay. That means, I take the determinant of the matrix Gy of x, I keep on taking at every point of time, take an absolute value of that, and if it is beyond certain bound, I know for sure that the matrix is non-singular. Okay. And then only I will update the control, otherwise I will not. So, obviously, when I am not updating the control, I am just holding my previous control or something, it may lead to performance degradation locally. So, you will not be able to track your commanded variable and things like that, but that will happen only locally. Okay. And then after you are out of that, that means after you are out of the singularity domain, then again this condition will hold good, and hence you can still be able to update your controller actually. So, what my recommendation is, like whether it happens or not, keep it as an integral part of your programming actually. Like whenever you want to implement a controller, just before updating the controller, have this check actually. Okay. Only when this check is passed through, then only you update your control, otherwise hold the previous control. Okay. I mean that will be true after your first time step, but first time step usually, if the first time step itself there is a singularity, then you have to really go back and think something else actually. Okay, so option is always there to reformulate the problem. That means if I have aimed too much or aimed too sharp a maneuver or something like that, I can lead to a lesser, I mean kind of not so highly demanding maneuver. That means I can do a nice turning instead of a sharp turning sort of thing. These are like reformulating the problem actually. Okay. Or I mean I can even think of some sort of adding some control surface in addition to what I have. I mean that is a design change fundamentally, and things like that. Okay. So, that these are like subjected to problems, subjected to capability of the vehicle and capability of the system, like that actually. Okay. But apart from this these engineering fixes and philosophical issues and things like that, there are also some advanced techniques to address this issue partly in the control design process itself. Okay. That means we are not going to talk too much on that in this class, but there are techniques available which will prevent this from happening. So, here we are just assuming, okay, we are just putting some sort of a condition and then hoping for the best. But these techniques what you are talking here will purposefully try to avoid this this singularity issue coming into your system actually. So, they will keep on monitoring some sort of a determinant rate and things like that philosophically, and then they will try to modify and telling that, okay, if you are approaching determinant approaches to 0, then probably that is not the right way to go, right direction to go basically. So, but more on that probably you can pick up some literature or something and try to see that actually. But fundamentally if there is no controllability in the plant locally, you cannot do anything actually. Okay. So, that is an issue that you should be aware of actually. Anyway, so coming back, my suggestion is invariably have this check in your implementation of the dynamic inversion controller before updating your control actually. Alright, next issue, what if the output dynamics is non-square? That means dimension of y is not equal to dimension of p. In that sense, gy of x is non-square actually. Okay. So, obviously we cannot talk about inversion of that matrix. Now, there are two cases may happen, that means first case is m is less than p, and the second case is m is greater than p. So, m is less than p means number of controllers are less than number of objectives. Okay. Number of independent controllers are less than number of independent objectives here actually. So, in that situation there is a great theorem which tells us that perfect tracking is not possible in general. Okay. That means only for limited objectives, that means like regulator design and things like that, you can do some sort of a manipulation of the variable. You select x2 instead of x1, so that you can attain your objective and things like that. One example we saw that in the last class also, that how do you handle this for a second order system and all that actually. But in general for arbitrary signal tracking, the theorem tells that it is not possible actually. You cannot demand an arbitrary signal and then tell me to track it unless and otherwise I have at least the same number of independent controllers as the number of objectives that you want me to track actually. Okay. So, that is that is the theorem that will accept it without proof actually. But anyway, so the case 2 is rather interesting, which tells you what if the reverse case. Okay. So, I buy that because I have not given you enough capability here when m is less than p, but suppose I give you more capability, m is greater than p, then what? Okay. So, obviously, you have more control capability than the demand actually. So, the certainly intuition tells us that it is possible, the tracking objective has to be met actually. But in addition to meeting the tracking objective, we can always put additional objectives because we have larger number of controllers, we have more number of controllers anyway. Okay. So, we can put additional objectives can be demanded in the design in general actually. So, and one such approach is what we call as optimal dynamic inversion. There are various ways of interpreting this problem obviously, and I will take you through one development that we in our lab have been using that. We have proposed this and then trying to use it actually. Anyway, so this is something like m is greater than p. So, what you let's go back to this entire design process and try to see where we are invoking this issue actually. So, if you go back and see this math, this is where we started with, that we have to enforce this E dot plus k equal to 0 and carry out the algebra. So, we substituted E equal to y minus y star, E dot is y dot minus y star dot, y dot is like that, we have derived it before, and then we will tell okay, this from here to here we cannot do that, because this I mean here to here is okay, but the step that we discussed last time, that we cannot solve a control directly taking g y of x in inverse, because g y is no more a square matrix actually. Okay. But I can always interpret this equation as a constraint equation. So, I have to find a solution in such a way that this equation is satisfied actually for whatever reason. So, this equation I will rewrite it that way, okay, and I will define this A and B for notational simplicity. Okay. So, that this is a time varying matrix A, this is a time varying vector B. So, the equation turns out to be something like A u equal to B, A times u equal to B. Just to remember that A and B are no more constant matrices and vectors, they are time varying matrices and vectors actually. But this equation is still valid actually, okay, just that from this equation we will not be able to solve for you directly, okay, but this equation itself is valid. So, I will interpret this as a constraint equation. So, if I somehow find a control solution satisfying this constraint equation, that means this equation is again satisfied, this equation is still valid, and I will have the tracking objective met anyway. Now, how do I find some sort of a solution for this? Remember, this is under constraint problem, because number of controllers are larger than number of outputs, that means number of free variables that you are talking is larger than number of constraints actually. Okay. So, this is under constraint problem. So, let me put additional objective for which I will take okay, I will let me if something is given to me or some problem demands that I will do something justifiable, something meaningful, then I will put that also as a tracking objective. But without that knowledge, I can always formulate some sort of a control minimizing problem actually. I will try to get a control solution for which this performance index needs to be minimized at all time. This is a quadratic performance index. So, I will try to minimize this control effort, okay, subject to this constraint equation that I am talking actually. So, this constraint equation guarantees tracking, and this objective what I have been talking about, this guarantees minimum control effort for that tracking basically. Okay. So, now we can see that this for any point of time, this is a standard kind of quadratic performance index with the linear constraint equation, and hence it is very rather standard to solve it using static optimization ideas and all that actually. So, we will interpret okay, this is my cost function to minimize, this is a constraint equation. So, that augmented performance index turns out to be j plus lambda transpose A u minus b, and then I have to satisfy both the equations together, del j bar by del e equal to 0 and del j bar by del lambda also equal to 0, and lambda is the dimension of lambda is same as dimension of y obviously, because it is coming from this constraint equation actually. Okay. Alright, so how do you do that? Suppose del j bar by del u, let us say you do, then this the first term you get r u, the second term you get A transpose lambda. So, r u plus A transpose lambda needs to be 0, and the second one if you do, this turns out to be A u minus b equal to 0, that means A u equal to b, which is nothing but the constraint equation again. So, these are all given here. So, first r u plus A transpose lambda 0, A u minus b equal to 0. So, these two equations needs to be solved together. So, let me solve for u from here. So, u is nothing but minus r inverse A transpose lambda, and then if I substitute that u here back actually, what I am getting here is A times that is nothing but b, A times u whatever u I have is equal to b. So, let me solve for lambda from here, and lambda solution turns out to be like that, and once I get a lambda solution I will put it back here in the control solution. So, my control turns out to be r inverse A transpose this entire matrix inverse times b. And this is possible because why is it possible? Because at the if you see this A lambda equal to b and things like that, this particular matrix A times r inverse times A transpose is certainly certainly some sort of a square matrix, and more than that because r is supposed to be positive definite here, okay, that is the requirement for some sort of a convex cost function and all that. What you are telling here, r needs to be positive definite, and again by a standard mantra sort of thing is we just take r is a diagonal matrix to begin with actually. Okay, so that means I mean this particular R being a positive definite matrix, R inverse is also positive definite matrix, and because of that A times R inverse A transpose is guaranteed to be positive semi definite matrix. It is going to be square, it is going to be symmetric, it is also going to be positive semi definite. So, that is how I will be able to talk about an inverse. All that I am assuming here is there is no, this positive semi definite means there is a chance of getting singular again also basically. So, that one what I am assuming here is this particular matrix is non singular here by assumption, but this is a square matrix certainly, and that is how I have avoided this issue of taking inverse of a non square matrix actually, that is the philosophy. So, anyway, so coming back this constant equation satisfy, I mean guarantees error dynamics, I mean the error of tracking goes to 0, and then this objective function that I am selecting also guarantees that I have a control minimizing solution for that. And the way I select for R that means let us say R I select R1, R2, R3 as diagonal elements and all that. Selection of this R1, R2 and all that will also give me some sort of a allocation technique basically, control allocation technique. That means, if I select R1 higher than the rest of the things, then this design will assure that U1 magnitude turns out to be lesser than rest of the things basically. So, that way I will be able to tune my control components using as a proper selection of R actually. Alright, so this is what we call as optimal dynamic inversion, because there is some sort of a optimal control allocation actually. Okay, that is the reason for that. And some useful features of ODI, optimal dynamic inversion, is as I told you already, the enforced aerodynamics is satisfied exactly. So, asymptotic tracking behavior is not compromised. ODI also gives a platform for optimal control allocation, as I also told you now. So, this can be done both time wise as well as location wise or component wise actually, because this R matrix what you are selecting here need not be kind of constant matrix, it can also be function of time. So, as time goes I can enlarge one component and shrink one component and things like that. Initially you might want to use some particular component larger, later you do not want to use it larger, and things like all that thing can be incorporated by making R as a function of time, also as a function of components of the various components actually, like R1, R2, R3 stands essentially stands for U1, U2, U3, I mean the magnitude of that, provided R is a diagonal matrix. Now, an interesting observation turns out that what if I select R as identity matrix. Now, if you go back and see this expression, and R is identity means R inverse is also identity, that means I will end up with something like A transpose inverse times B. So, this A transpose inverse is nothing but pseudo inverse actually. Okay. So, if I take pseudo inverse B, so without without all this algebra and all, I just land up here, this is a non square matrix. So, I just talk about pseudo inverse, and that is also an optimal solution in this in the sense that R becomes identity, that means equal distribution of control effort in all channel actually. So, without understanding all the details, if somebody takes a pseudo inverse for that, it is also okay, because what he talks about is some sort of a right pseudo inverse and things like that, and that is good because this is a under constraint equation. If it happens to be over constraint equation, pseudo inverse solution is never good actually. We have discussed that in matrix theory also. So, those of you forgot that, you can go back to the matrix theory lecture and then try to recapitulate some of that. Anyway, so this is what we are talking, that is just as a special case R equal to I, then you can end up with a graceful degradation to pseudo inverse design. But otherwise we retain more generality here, because you can the fact is we can it gives us a platform for optimal control allocation both time wise as well as location wise or component wise basically. So, that is the beauty of this ODI basically. And also just a comment sort of thing, this ODI idea can be extended to distributed parameter system control, because that is where you have this infinite modes and things like that comes. So, invariably you will end up with under constraint problems and all that actually. We will not talk too much on that, but so those of you who want to study more, these are the references from our research output. And first one is it talks about some sort of a biomedical problem and all, but there is a generic section on this paper which talks about this theory as a generic framework actually. Okay. And then this second one is you can think of as some sort of an extension to distributed parameter systems. Okay. How do you use this ODI concept for that actually? Okay. So, let us move on to the next topic, the next big topic. The question here is the internal dynamics always stable? Okay, that is a major issue. So, these last two issues were the primarily big issues that we that was like why this design was not very popular for a long time. Okay. All right. So, is the internal dynamics always stable? Answer turns out to be not necessarily so again. Okay. And obviously, if the controls are, I mean if the internal dynamics is unstable, unstable, then obviously it is somewhat like I mean operation success what patient died sort of thing. I mean that means the control solution is meaningless, because the dynamics in the rest of the space is going unstable. Okay. That means your system as a whole can behave very badly actually. Your output tracking may happen, but your system may even burn out, even crash and things like that. For example, if you talk about let us say turning, I mean turning an aircraft, maneuvering and things like the lateral dynamics, and if lateral dynamics you simply turn a circle sort of thing. Okay. And while taking a circular turn, your longitudinal dynamics becomes unstable. That means height can be negative. That means your I mean height can go unstable. It can come the entire aircraft can crash actually. So, as far as lateral dynamics is concerned, I mean that you can, I mean if you project the trajectory, probably it will still be a circle, but if you project this I mean trajectory from top, actually it will still be a circle, but the aircraft will essentially going some sort of helical path. Okay, because and then altitude is dropping and finally it is crashing actually. Okay. So, no point in having such sort of design where you can only concentrate about output actually. So, invariably what it turns out that the moment you talk about dynamic inversion design, I mean all that we are discussing here is input output linearization by the way, and there is another parallel concept called input to state linearization, which we are not discussing here at all actually. Okay. So, for that design the internal dynamics is not an issue, but the input output version is very practical. That is what a lot of people use in variety of applications, and that is where internal dynamics needs to be explicitly addressed. That means any design that you propose based on dynamic inversion, you should take extreme care and to explicitly demonstrate that internal dynamics remains stable. It should never be an assumption actually. Okay. So, coming back, the control solution is meaningless unless this issue is addressed explicitly. Okay. So, there are some standard results. First result tells us that if the relative degree, that means the total relative degree, that is what I am talking. If the total relative degree of the problem is equal to the number of states, then the internal dynamics is stable. And again what is total relative degree? Like relative degrees of each of the components of the output vector, you just add them up actually. Okay. If that total relative degree turns out to be equal to number of states, that means there is no internal dynamics actually. Every dynamics, every space, I mean dynamics in every kind of dimension is visible in the design. So, the internal dynamics is not there, or in other words internal dynamics is always stable actually. Okay. Everything goes to the output vector actually. Alright. Now, the why it happens by the way, because if I enforce a stable second order dynamics, then not only may let us say like E double dot plus something like k 1 times E dot plus I mean if I write it somewhere like let us say if I assume this E double dot plus 2 zeta omega n E dot and things like that, 2 zeta omega n E dot plus omega n square E equal to 0, then this design not only enforces that E goes to 0, it also enforces that E dot goes to 0. Together it happens actually. So, the moment I take a second order aerodynamics, I have taken care of 2 dimensions actually, and similarly if I take care of those many dimensions, then I am done actually that way. If the total relative degree turns out to be equal to the number of states, then I have taken care of the stability of all the dimensions actually. But that is a very lucky sort of situation. That means many times it will not happen that way. Okay. So, extreme rare cases only you will end up with those situations where you have enough controllability for example actually. Okay. So, for example, if you talk about only let us say attitude stability of a satellite with 3 axis control, independent control, then for each of the axis you can think of it as some sort of a double integrator, and then theta and omega in each of the axis will go to 0, means some stable values actually, but that is a very rare situation that every problem will not admit that kind of solution actually. So, what next? The next is there is something called zero dynamics, and the theorem tells that asymptotic stability of zero dynamics is sufficient for local input to state stability of internal dynamics. I mean these are concepts. I mean more details if somebody wants they can always see Slotin and Lee book. There is a nice chapter for this these discussions and all that actually. But anyway, for, zero dynamics means what you define as zero dynamics is something like that. You purposefully take that y star that we discussed as 0 for all time actually. So, irrespective of whatever command that you are giving, you formulate a parallel artificial problem for which y star is 0, y star dot, double dot, all that are 0 actually, and then redesign your control. Okay. So, with respect to that control, because what is that? I mean that has become completely independent of the output command that you want to track. So, and hence that becomes some sort of an intrinsic property of a system actually. Okay. So, that way it is that is what we want to call that as zero dynamics. Okay. And if the zero dynamics happens to be stable, okay, because remember after the tracking variable goes to 0 and things like that, what you are assuming is that 0 command has already been tracked actually. So, whatever is left out is nothing but what is called a zero dynamics actually. The difference between zero dynamics and internal dynamics is for internal dynamics you are actually giving the desired command, for zero dynamics you are artificially giving a 0 command. Okay, and hence it becomes some sort of a homogeneous system actually. Okay. So, the zero dynamics remains if the theorem tells us that if the zero dynamics is stable, okay, that means asymptotically stable and things like that, which can be kind of assured using Lyapunov theory, because it is some sort of a homogeneous system dynamics. And this Lyapunov theory and all we are going to discuss next class actually, next class onwards, then we will see that actually what are the implications. But anyway, if the zero dynamics happens to be asymptotically stable, then it is sufficient for to tell that the internal dynamics is stable in the input to state sense. That means internal dynamics is guaranteed to be stable actually. Okay. So, alright. So, that is what it is, but if that is all, sometimes also it is difficult for complicated problem, because you will end up with some sort of a complicated zero dynamics. How do you show that? And one thing to show that is okay, the zero dynamics can be linearized about whatever your the nominal trajectory, and keep on showing that the linearized zero dynamics will remain stable, and then you invoke this what that indirect Lyapunov theorem, which tells okay, if the linear system around some point is stable, then nonlinear system is also stable locally. I mean that is the way to do that. Otherwise directly you can invoke this Lyapunov's direct theorem, then that is the best. But even if you do not if you may not be able to do all that, then in other words if the analytical justification is not possible, okay, then extensive simulation studies must be carried out actually. Okay. So, at least from the simulation studies you have to show, I mean that is the Monte Carlo simulation and things like that, that even if I take the various signals to track and things like that, then internal dynamics still remains stable actually. Okay, so this zero dynamics concepts also gives us this this idea of what is called minimum phase systems, and that by definition these minimum phase systems are nonlinear systems for which the zero dynamics is stable. Okay, so if the zero dynamics is stable, that means the internal dynamics will be stable, and hence there is no problem actually. And this minimum phase, the non-minimum phase and things like that we study in classical systems, that means the right hand side zeros and things like that those of you know, and we have also discussed some of that in the very beginning classes actually. So, if there is a right hand side 0 sort of thing, it excites some sort of a non-minimum phase behavior and things like that actually. Those concepts are related to that also. Okay. That means what happens there is in the right hand side whatever zeros becomes right hand side pole for the internal dynamics actually. Okay. That is where the connectivity comes and all that. So, this definition what you see here is not very different from what you already know actually that way. So, if the system is there is a system for which the zero dynamics is unstable, that means that is not a very good candidate for dynamic inversion actually. Okay. So, there are remedies to do that actually. So, is there a procedure for tracking control? The next question is obviously, is there a procedure for tracking control design for non-minimum phase systems? That means for which the zero dynamics is not really good, and answer turns out to be fortunately yes, you can do that actually. And this is something called output redefinition technique. Okay. And this technique is available for which the internal dynamics is first made locally stable before achieving the tracking objective. So, first you make sure that the internal dynamics remains stable, okay, and then on that system you try to design some sort of a tracking controller actually. Okay. So, your control objective will be split into two sort of roles actually. Okay. And some time back we discussed that also, like while developing aircraft you can make sure that it behaves like another aircraft and then design a controller for that aircraft, that kind of idea basically, philosophically. So, first you make sure that your the controller will first make sure that the internal dynamics is locally stable and then try to attain the tracking objective. Okay. And in that attempt you may not be able to do a perfect job also, by the way, but approximate job which is very close to what you want is also alright actually. Alright, and that is what more on that you can study on these two papers. This is the second one, is probably the the seminal paper which first proposed all that, and this is probably a little bit math oriented and good for academicians and further research, things like that, but for engineering things and understanding this technique and all, I will probably suggest the first one actually. Okay. Anyway, so what is philosophically, let us try to understand this little bit at least and then before stopping this discussion. So, the key idea for this output redefinition technique is do not aim for perfect tracking, but approximate tracking is okay. Okay, that means, but the approximate should be very close to what you really want, that is in that sense actually. And so what is the idea there? Let the original output be some y equal h of x, which has an unstable zero dynamics. So, what do you do then? We define y1 which is h1 of x such that the resulting zero dynamics for y1 tracking is stable. We do not aim for y tracking, we aim for y1 tracking instead. And what you do is, after this objective is met, we go back and see that the design the controller such that y1 goes to yd of t or y star of t exactly. Then this implies good tracking of the original output provided certain conditions are met actually. Okay. So, what is going on here is something like this. We make sure that y1 tracking is achieved, then go back and analyze how much error will make with respect to y actually instead. That particular design what you are proposing for y1 tracking, is it really good or bad for y tracking? That is the way. And it turns out if the y1 is selected properly in a judicious manner, then y and y1 may not be too bad actually, this approach may not be too bad. How do you do that? Let us see a small example. The example is again I have taken from Slotin-Lee book, Applied Nonlinear Control, Slotin and Lee. Anyway, let us talk about some sort of a linear single input single output system for which you can represent it using transfer functions actually. So, if your y and u are related by this transfer function, then obviously there is a right hand side 0 here, s equal to b, for which and clearly there is a problem of internal dynamics, zero dynamics is unstable obviously. Okay. So, the system has a right hand side plane 0 at s equal to b, and then to avoid that what we will do is we will simply take out this and formulate a y1. Okay. Remember, b0 does not contain a right hand side 0 actually, that is our assumption. Okay. So, we define an y1 and make sure that y1 tracks our objective, everything is met actually. Now, what if we will analyze what happens to y basically, that is the objective. So, y1 has gone to yd already, yd turns out desired actually, this is the yd and y star are same. That way. Okay. So, y1 has gone to yd, and so what you do and then what we do is we analyze the case when y1 is equal to yd. y1 has gone to yd, that is the assumption actually. Now, what is y? Y and y1 are defined like that. So, obviously, y and y1 are related like that, right. Y1 is defined like this. So, y is defined like that. So, y is this times whatever this times y1. Okay. So, that is what you have written here, y is nothing but that 1 minus s by b times y1. So, obviously, this y1 has gone to yd already. So, instead of y1 I can substitute yd, and then error is defined that way. So, right. So, that means this I can define this see this derivatives and all, if you see that actually. Okay. Right. This is see, remember this one is yd minus yd dot by b. This expression, if you expand it, nothing but yd minus yd dot by b, as multiplied by s is nothing but time derivative actually. So, yd minus yd dot by b minus yd, that means you will end up with this expression actually. Okay. So, what it tells us, the error with respect to y and yd, okay, will remain bounded as long as y dot t is bounded, okay, because b is a constant number after all actually. Okay. As long as y dot t is bounded, then this error will remain bounded actually. Furthermore, if b is large, okay, that means this bound is going to be smaller and smaller actually. Okay. So, that is one thing. Now, let us reinterpret this same problem defining y2 instead. Okay. y1 was defined like that. Let us formulate a problem 2 with y2, where not only we will cancel this, but we will add 1 plus s by e in the denominator. So, that is what we have not taken the 0 part, but we have added a pole identically in the left side actually. Okay. Then what actually? So, you can again do the same analysis again, but this time it is y double dot, because s square will pop up. Okay. So, this e of t becomes a function of y double dot now actually. So, this e of t will remain bounded as long as y double dot is bounded, and if b square is larger this time, okay, then then obviously e will be smaller and smaller. Now, naturally it turns out that okay, this selection probably is better than that, but nonlinear control you have to be slightly more careful. You have to kind of see these expressions very carefully, and this analysis is true. So, out of these two choices, y2 is better, provided this condition holds good, because it may so happen in some problem that y dot this condition may not be valid actually, then your y1 selection is better, but if this condition holds good, then your yt is better actually. So, these are like some of these ideas that you can exploit. Another approach to deal with non-minimum phase, first of all is like neglect terms in containing the input u while doing successive iterations of the output until number of successive differentiation becomes n actually. This is a trick that we regularly exploit in aerospace design, by the way, okay, because if you see the 6-top equations that we discussed, we derived also and things like that, your v dot w dot and all that will contain a term from control surface reflections as well, but these are not very powerful. So, if you really want to synthesize your controller directly from v dot w dot for the guidance purpose and things like that, then your rotational dynamics will go unstable actually. So, how do you do? Normally we take instead of v dot we take v double dot instead, and one of the design we will discuss in the one of the classes later probably, okay, where we will try to wind up this neuro-adaptive design with a aircraft control and all that actually. So, instead of v dot we take v double dot and then neglect the control dot out there, just simply assume that is 0 or things like that, control effect is 0. Then you go to the next level of differentiation, and then v double dot will contain r and things like that. So, w double dot will contain expressions of q, body rates basically, and for that q dot, r dot and all, there is still a control will appear, and because of that the control is powerful for rotational dynamics and all that. So, at that level we want to use the dynamic inversion, we want to invert the matrix actually. So, these are the concepts that you have to, especially in aerospace applications we use it regularly. So, what is the idea here? If so at particular output level, let us say your control appears, so do not get unnecessarily happy, because that particular channel the control may appear, but it may be very less effective. Okay. So, in that sense you can very well neglect the control variable and do one more derivative, and then hope for the best, in the sense the next level of derivative control can still appear one more time, because you are talking derivatives of other state variables and all that, and at that level the control may become powerful actually. So, you will have good controllability at that level actually. Okay. So, then you use the dynamic inversion at that level of differentiation. So, that what you are telling here is you are exciting more level of more and more output derivatives actually. Okay. So, that is philosophy that we use regularly actually. Okay. And as I told, this approach works as long as the coefficient of u at the intermediate steps are small. That means the system is weakly non-minimum phase. Okay. If the system turns out to be weakly non-minimum phase, then this idea works wonderfully, and normally these aerospace problems it works very well actually. Other ideas, modify the desired trajectory. That means, if you have really assumed a sharp maneuver, do not assume sharp maneuver, vehicle is not capable. So, you use some sort of a benign maneuver, things like that. and then the other alternative is modify the plant itself. That means, you go back and redesign the plant itself actually. It may be possible by relocation of the actuator sensors or by adding more number of actuator sensors in the loop actually. So, you are altering the transfer function or you are altering the system dynamics that you are looking for actually. Okay, so, it may be also possible by physical modification of the plant. That means, for example, placing the control surfaces at different locations in an aircraft. So, these are like bigger issues and all that. So, in that sense your plant itself you are changing. So, in this first one you are modifying your objective, the second one your plant itself you are changing actually. Okay. This is the way to do that. The next big issue, okay, that is the fourth one what we discussed before, is the dynamic inversion design sensitive to modeling and parameter inaccuracies, and the answer turns out to be very much yes actually. Okay. And the solution is because of this particular big issue, this design was not very popular for a long time again, and now people know how to handle this actually. So, if it becomes a big issue in your particular design, then they tell okay, let us not use dynamic inversion as it is, but let us try to augment this using more robust control design or adaptive control design techniques. That means, you will see DI plus H infinity, DI plus adaptive control, DI plus Neuro-Adaptive, like that actually those ideas. And one popular approach that we propose and we use in our lab also like that is what is called Neuro-Adaptive control design. Okay, that is adaptive control design philosophy, where neural network is also in the loop actually. Okay. And this particular design we are going to discuss extensively anyway, okay, in the subsequent lectures. So, I am not going to talk too much on that, but philosophically speaking, why do you need this thing, where this issue comes, so why do you need it, parameter inaccuracy, modeling inaccuracy and all that. So, motivations for NA design, Neuro-Adaptive design is as I told, the perfect system modeling is difficult, okay, and source of imperfections can arise from unmodeled dynamics, that means missing algebraic terms in the model, or inaccurate knowledge of the system parameters. You really do not have exact number values of the parameters can keep changing also. For example, mass of the aircraft keeps changing because at least fuel keeps on going out actually, or mass of the rocket changes very rapidly rather that way. And you can also have change of system parameter or system dynamics during operation. It need not remain constant forever actually. So, the adaptive control design should be able to learn the unknown function through the neural networks and then compensate for this unknown error. So, the entire plant you know large part of the plant, some portion you do not know. So, that whatever unknown plant or unknown portion pops up, that portion needs to be learned, and that unknown that inaccuracy whatever you are talking is going to throw some sort of a unknown function in the system dynamics, and that unknown function needs to be learned through the neural network, and then once you learn it you can compensate for that actually. So, philosophically speaking, the issue is something like this. So, let us say x dot equal 2 sin x, that is actually known part of the system dynamics, but 2 is not 2, but for some reason it is 2.1. That 0.1 we are not knowing what is this 0.1 or minus 0.1 or minus 0.2 whatever it is, that is not known to us. So, because this 2 has become 2.1, x dot has become like this. So, this additional nonlinear function has evolved because of parameter inaccuracy. Because of parameter inaccuracy you had an unknown function and all that. So, this particular function if I analyze a little, I can tell oh this part sin x can be some sort of a basis function, and delta c turns out to be some sort of a unknown coefficient. So, if I learn this function using this basis function sin x or some other basis function can also hold good, then I actually know this unknown part after learning. So, after learning I will not use only 2 sin x, but I will be able to use entire thing actually, because because this system dynamics will no more be completely unknown basically. That is the whole idea there. We will talk about that in subsequent classes anyway. So, summary of this entire dynamic inversion design. DI offers several advantages. First of all, let us try to recapitulate again. It is a nonlinear design and no linearization of system dynamics is necessary. It is certainly a promising substitute for gain scheduling philosophy, and quite often a constant gain is found to be satisfactory, even though limited amount of scheduling can still be done actually. It assures perfect tracking, that means asymptotic stability of aerodynamics under the ideal assumption that perfect knowledge of the system dynamics is available. and the DI offers a closed form solution for the control and hence can be easily implemented for online applications. But when you implement DI design, one has to be careful about the following important issues. First of all, the non-existence of matrix inversion, and if this is a local problem, do not update the control. And there is a stability of internal dynamics issue. If the analysis fails, then either for reformulate the problem or opt for output redefinition technique. There are options available to you. And robustness with respect to modeling inaccuracies and all, you can augment the DI design with a Neuro-Adaptive technique actually. Okay. So, with that I think I will stop this lecture. Thanks a lot.